So now we have a basic understanding. Okay, sampling this, you have the primary population. Population has some distribution. Okay, and then we take normally we take only one sample, but to understand the sampling distribution, we assume that we're going to take all possible samples of a given size n, and then compute x bars for all of those samples, and you have a secondary population of x bars. And sampling distribution simply means what the probability distribution is for this second population. And we have already seen the central limit theorem concept. So if this population is normally distributed, okay, I'm restating central limit theorem and sampling distribution very quickly. If this is normally distributed, the primary population is normally distributed, the secondary population of x bar will follow a normal distribution, same mean, and standard deviation will be sigma over square root of n, and that is called standard error. Now, if this population is not normally distributed, or we don't know what the distribution is, then the population of x bars will follow approximately normal distribution and will become closer and closer to normal as the sample size increases, with mean mu the same as the original population and standard error sigma over square root of n. So this is in essence the whole topic covered in chapter 7. So for example, suppose you have a sample of 50 students from your college regarding mean GPA. Okay, so if you obtained many different samples of 50, you will compute different mean for each sample. So we are interested in the distribution of all the potential mean GPA of those samples. So that's your sampling distribution. So let's look at even a small and more concrete example. Suppose we have a population consisting of just 4 people. That's it, just 4. And the random variable of interest is age. So now we have the age of these 4 people, 18, 20, 22, 24. That's it. This is the whole population. Yeah. And if you randomly select one person, what will be the age of that person? Okay, it'll be either 18, 20, 22, or 24 with equal probability. So it isn't uniformly, the probabilities are uniformly distributed in this original population. So the original population has 4 individuals, okay, and it is uniformly distributed. Okay, so this is what the distribution will look like, and then of course we can find the mean is 21, and since this is how we have defined the population, this 21 is the population mean, and we can compute the standard deviation, and that is 2.236. So this is the original population. And let's suppose that we take samples of size just 2. Okay. So there are 4, and 4 combination 2, there are totally 16 possible observations. So we are assuming that we are sampling with replacement. Okay, so that is, you take one person, look at that person, put that person back, and then randomly select one more person. So we have 16 possibilities, and here are the samples of all the 16 possibilities. Okay, so 18 and 18, 18 and 20, 18 and 22. So we have enumerated all possibilities. So these are the all possible samples, and if you compute the sample mean of each of them, so here are the sample means of all possible samples of size 2. Okay. So now what is the probability distribution of these sample means? So if you now compute the probability of these sample means and look at the sample mean population, it looks like a normal distribution. So it's no longer uniform. Okay, if you compute a frequency distribution for x bars, okay, and then plot the x bars histograms, and this is what it will look like. So this is a dramatic illustration of what central limit theorem tells us. So even though the original population is uniform, even for a sample size of 2, x bars end up being uniform, normally distributed. Uniform distribution is kind of a symmetric distribution, so this is very quickly x bar follows normal distribution. But if the original population is unknown distribution, sometimes n has to be larger than 2, obviously. Okay, so let's compute the mean and standard deviation of this sample means, the population of sample means, and it turns out, of course, mu of x bar is 21, and sigma sub x bar is now 1.58. So here are the two populations, the original population, mean, standard deviation. Now the sampling distribution of x bars, okay, normal distribution, same mean, and sigma sub x bar is sigma over square root of n. So here is the central limit theorem. If population is normal with mean mu and sigma, the sampling distribution for x bar is also normally distributed. Mean mu, sigma sub x bar is sigma over square root of n. And then the z values can then be calculated in this fashion. Okay. Now sampling distribution properties. So it is called, this property is called unbiased. So the mean of x bar is the mean of x itself. So therefore x bar is supposed to be an unbiased estimator of mean mu. Okay. As n increases, sigma sub x bar decreases. So for larger samples and smaller samples. Okay. Now even if the population is not normal, the sample mean will follow approximately normal, and the approximation will become closer and closer to the actual normal distribution as n increases, and mu sub x bar is mu, sigma sub x bar is sigma over square root of n. So we can look at central limit theorem in a picture format like this. So whatever the underlying population may be, as n increases, the population distribution of x bar will become closer and closer to normal. So here is another way of looking at it. So if you have a distribution for x, which is not normal, obviously it is not symmetric. Now for smaller sample sizes, okay, the skew will continue, but it will slowly become closer and closer to normal. And for larger sample sizes, then you will see that the distribution of x bar will be very close to normal, indistinguishable from normal. So at what point do we get indistinguishably normal distribution? So for most distribution, if sample size is 30 or more, then the sampling distribution will be normal or very, very close to normal. You can't even tell them apart. Okay, so n greater than or equal to 30 is considered large sample. Now, if the underlying population is kind of a fairly symmetric distribution, even if it is not normal, like for example uniform distribution, even smaller sample sizes will do. N greater than or equal to 15 it will give you extremely accurate approximation of normal distribution. So n equal to 30 is not something, n is greater than or equal to 30 is not a kind of a, hard and fast rule. It's only a thumb rule. You can be a little flexible with that. So for a normal distribution, the sampling distribution of the mean is always normally distributed. Okay, the original population is normal, sample size doesn't matter. So this n greater than or equal to 15 or n greater than or equal to 30 and anything in between is only if the underlying population is not normal. Okay, here is an example. Suppose if you have a population with mean 8 and standard deviation is 3. And suppose we take a random sample of size 36. Now what is the probability that this sample mean is between 7.8 and 8.2? Now since n is 36, we don't care what the original population is. We know x bar is going to be normally distributed. So we can use the normal distribution method to find this probability. So find the z for 7.8, find z for 8.2, and remember to use sigma over square root of n as the standard error for sample mean. Okay, this is the original standard deviation, but we are now talking about probability of sample mean, and the standard deviation for sample mean, which is also called standard error, is sigma over square root of n. So here sigma over square root of n is 0.5. So find z is 7.8 minus 8, the mean, divided by sigma over square root of n, and then the right hand side 8.2 minus 8 divided by sigma over square root of n. So you get the two z values, and then you find the table value and find the probability. So something like this. The population distribution is unknown. We take a sample, and the sample distribution follows normal distribution, and we want the probability from 7.8 to 8.2. Translate that to standardize it to z values and find the probability using the normal table. Now let's look at an Excel example.